Right, today I will talk about the second leptogenesis to explain the large discrepancy between the baryon and the lepton asymmetry. This talk is based on our recent papers and collaborators the Yelins, Kazakis and Hesson. In the universe, there are more matters compared to antimatters. It is called the baryon asymmetry of the universe (BAU). The baryon asymmetry of the universe (BAU) can be parameterized by the eta b, and the order of zeta b is 10 to the minus 10, which can be obtained from the BBN or the CMB. To generalize the baryon symmetry, the following Sakharov condition should be satisfied. Standard model satisfies this condition, but it's not enough, so there are several baryon models introduced. Like as electroweak baryogenesis, GOTs, black-dime baryogenesis, and leptogenesis. Recently, the MPLUS reported helium-4 abundance observations which can be used to evaluate the lepton asymmetry of the universe (LAU). The order of the eta L is 10 to the minus 2, which is extremely large compared to the BAU. So to explain such a large discrepancy between the lepton and the baryon asymmetry, a new baryogenesis model should be necessary, and among the several models, leptogenesis can help this large discrepancy because in the leptogenesis model, the lepton asymmetry is generated first and it translates to the baryon asymmetry. The leptogenesis occurs with the decay of the heavy matter neutrino capital M. It decays to the different decay modes, lepton Higgs and anti-lepton and anti-Higgs. Then the lepton asymmetry is generated in the interference term of the tree level and the loop level diagram, and it transits to the baryon asymmetry via the parallel process. This parallel process decouple at the electroweak symmetry breaking. So after the electroweak phase transition, the baryon symmetry becomes fixed, and this value is just determined. We can consider that the leptogenesis after the electroweak symmetry breaking in the late time universe. Then the generated lepton asymmetry cannot be transited to the baryon asymmetry because the parallel process is allowed to decouple. So the baryon asymmetry cannot be changed, but the lepton asymmetry can be generated more. So such a leptogenesis in the late universe after the electroweak symmetry breaking can help the large discrepancy between the lepton asymmetry and the baryon asymmetry. So we consider the two modes of the leptogenesis, and such a second leptogenesis scenario require the secondary production and the decay of the heavy matter neutrino capital M. To realize the second leptogenesis, we adopt the wave dark matter. It has the ultralight mass K from the 10 to the minus 10 electron volt, the early electron volt. The lower bounds come from the Lyman upper Bohr state, and the upper bounds to have the longer de Broglie waves length rather than the interparticle separation. Wave dark matter build satisfies the following equation of the motion in the expanding universe, and the one double friction term is large, the scalar field pi is the was frozen, but if the Hubble friction is smaller than the dark matter mass, then it has the oscillating behavior. And the oscillation amplitude is proportional to the root of the law, where the law is energy density. So the amplitudes that decreased over the cosmic history with a proportionality of a to the minus 3/2. Here is a as scale factors of the universe. So if we consider the coupling between the wave dark matter pi and the heavy matter capital M, and the mass terms are generated from such oscillations of wave dark matter, then the mass term of the heavy matter neutrino can evolve through the cosmic time. So the amplitude is proportional to the T to 3/2, where T is the universe temperature. And we consider two kinds of term. The first term is the Bayer term M0, and the second is the mass variation term, which is arised from the coupling with the wave dark matter. So the heavy matter neutrino capital N get the temperature dependence. We consider two kinds of term. In the extremely early universe, when double friction term is larger than the wave dark matter mass, then the heavy matter neutrino mass was frozen at M star. And when the wave dark matter starts oscillations, the temperature starts decreasing, and it got the T2 derivative proportionality. And at the specific temperature Tn, below the Tn, the mass variation term is negligibly small compared to the bare mass term. So the heavy matter neutrino mass show that the following behaviors. In the early universe, they are constant and decreasing due to 3/2 slope, and it becomes constant again below the specific temperature Tn. And the decreasing slope of the mass terms is a T2 which is more steep compared with temperature. So the hierarchy between the temperature and the mass can be changed. So here in the plot, there are several times which is the temperature is larger than the mass, and at some moment temperature becomes smaller than the mass. So when the temperature is larger than the mass, the production channel of the heavy matter neutrino can be activated. So, but when the mass term is larger than the temperature, a production channel is suppressed by the Boltzmann factors, and the heavy matter neutrino and get the decay. And there are two moments of the large temperatures and two moments for the small temperatures compared with the mass, so that it can realize the secondary productions of the decay as shown in the plot. Here is a parameter space of the second leptogenesis. The orange regions are constrained to avoid the dominant coupling of the wave dark matters and avoid the normalizations of the wave dark matter by the scattering with the heavy matter neutrino. And the blue region is a naive condition for the second leptogenesis, but this is not exactly requirement of the secondary production of the decays, because it is just considering the hierarchy between the mass and the temperatures. So we solve the following Boltzmann equations, which is the density matrix form. Here are the two kinds of the equation. The first one is the number for the number density of the heavy matter neutrino N1, and the second one is the B minus asymmetry. And we insert the effect of the temporal dependent mass of the heavy matter neutrino to the boxed quantity, decay term D, scattering term S, and the Gaussian term W, CP asymmetry epsilon, and the equilibrium density. Among the several quantities, the equilibrium density is important. It gets the Boltzmann suppression factors when the mass term is larger than the temperature. In the our benchmark points, when the jet is variable jet is near than the one, then the temperature mass is extremely near, and it makes the Boltzmann suppression factors can be negligible. So as shown in the jet is near to 10 to the minus 2, the equilibrium density, the dashed line in the plot, it gets the suppression, but when the jet is near the 1, there's no suppression factor, so the equilibrium density can be as large as again. So if we solve the first Boltzmann equation for the number density of the neutrino, the result are things like that. The blue curve, when the blue curve goes up, then the heavy neutrinos are produced, and when it goes down, it decays. And we can see that in our benchmark point, the secondary productions and decay occurs by the temperature-dependent mass of the heavy neutrino. And in our scenario, the heavy neutrino mass varies, so the decay channels changes after electron asymmetry breaking. Before the phase transition, the typical channel is a mass last lepton and Higgs double modes, but after that, the N decay to the mass of on-shell boson and other lepton. But after that, the heavy matter neutrino mass, capital M, is smaller than the Higgs mass or double jet boson mass, then such channels kinematically forbidden. So the dominant channel is changed to the leptons and the meson modes. So in each cosmic period 1, 2, 3, we can see that there is a discontinuity when the decay channels changes. And for the scattering channel, because the mass term of the matter neutrino can be touches the jet boson mass, so it can provide a resonance behavior. So as shown in the light plot, the orange curves, the scattering channel show that the resonance at that moment. And there's a CP asymmetry which determines how much the lepton asymmetry is generated. And in our scenarios, the scale of the mass is relatively small. So to generate the inner baryon symmetry, we use the resonant leptogenesis. Here is the resonant factor, so which becomes the CP symmetry epsilon maximal when the resonant condition is satisfied, as baryon is the almost degenerate mass of the Heavy-man neutrinos each generation. And in our case, the Heavy-man neutrino evolves over the cosmic time for its mass. So in the early universe, we can set the resonant conditions are not satisfied exactly, which provides a relatively small CP symmetry and the baryon symmetry. And after that, by studying the bare mass term mass difference for the generation satisfies the resonant condition exactly, so the CP symmetry epsilon becomes a maximal and they generate the lepton symmetry compared to the largest baryon symmetry. So we solve the baryon-Boltzmann equations at the following benchmark point of the several parameters for the wave dark matter, having neutrinos and the complex spaces in the active star mixing matrix in the Casas parameterization for the Yucca matrix. So here is we just blue curves are number density, the density curves are equilibrium density, and the red curves are P-minus symmetry. And we said that at the parallel decoupling with the electron phase transition, the baryon symmetry is bit to the observed value, and we can see that the lepton symmetry is relatively larger than the baryon symmetry. And we can evaluate the eta B and eta L by multiplying the parallel factors and the photon dilution factor. And the lepton symmetry in our benchmark point is slightly smaller than the value, but it can explain the discrepancy between baryon and lepton symmetry. So we adopts the temperature-dependent mass of the Heavy-man neutrino by using the wave dark matter, and they can realize the second leptogenesis, and it can explain the baryon and lepton symmetry discrepancy.